All right, let's get started. Good morning, everyone. Welcome to the BR seminar series. I'm honored to introduce our today's speaker, Dr. Julia Gale, who is talking about a characterization of hydraulic fracture in a slant core from the hydraulic fracture test site project in the Wolfcamp Formation, Midland Basin, West Texas. So before we start, let me give you a brief introduction about Julia. Julia Gale obtained a PhD in structural geology from Exeter University in UK in 1987, working on the Archean of southern West Greenland. She taught structural geology and tectonics for 12 years at the University of Derby, UK. Julia moved to the University of Texas at Austin in 1998, where she is a senior research scientist at the Bureau of Economic Geology in the Jackson School of Geosciences. Her research focus is on natural fracture characterization and prediction in shale and carbonate hydrocarbon reservoirs. So with that, I would like to hand it over to Julia. Julia, thank you again for joining us today, and the floor is yours. You're welcome to share your screen with us.
Okay, yeah, I'll just say hi to everybody first. Thank you for joining. I know I guess, hi Frank, I guess I need to update my little bio because it says my focus is on natural fractures, and here I am talking about hydraulic fractures. So, but yeah, the emphasis has shifted a little bit as I've gone through my career. So I'm gonna just share my screen. All righty, so let's get going then. So as Sahar said, we're going to be looking at the hydraulic fracture test site, hydraulic fractures in particular. I will mention the natural fractures, and I need to acknowledge my co-workers. Myself and Sarah Elliott were the ones who did most of the work in terms of collecting the data sets. And then Bethany Ryzak, who's on the call, she is my master's student. I'll mention her in a minute. And then Steve Laubach came down several times and had a look at the results and you know, always provides insightful input to anything we do related to fractures. So that's the title, and let's get going. And I'm just trying to see if I can advance my slides, and for some reason it doesn't want to advance. Let me just see if I can restart that, and there we go. Okay. So we're going to just have a little bit of background. Some of you are very familiar with this project, and some, this is probably the first time you're hearing about it. So I'll just say something about the background for the project and the motivation for why we did the work we did. And then a short section on the methods. And then I'm going to spend most of the talk looking at some of the results that we got, especially for the hydraulic fractures, a little bit on natural fractures, and also say something about reactivation and proppant distribution, and then some conclusions. So this map here is taken straight out of Jordan Shidobka's project overview paper. There was a series of papers presented at ERTEC in 2018, and this is one of them. This gave a kind of a project overview, and you can see the hydraulic fracture test site, HFTS. Let me just see if I can do my laser pointer here. So here's the HFTS location in the Midland Basin in Reagan County, and we're in the Wolfcamp Formation with the core that I'm going to talk about. And as I say, there was all these papers in 2018, that's a resource, and then the project was partly funded by Lateral, DOE, and partly funded by a consortium, the Hydraulic Fracture Test Site Consortium of companies. And so the Lateral site here that I've listed gives a background as well. So what I've done here is to just take a snapshot from another of these papers. This is from Tanner Wood's paper, again from that 2018 group. And what it shows is, in the top here, is a gun barrel view of the well pad. And what you've got is these 11 wells. We're looking along the length of the wells. They're horizontal wells. And in the top layer that are labeled some number and then U, so 3U, 4U, 5U, 6U, 7U, and 8U, those refer to wells that were stimulated in the upper Wolfcamp. And then there's 5 that are stacked down below them in what's variously described as a chevron pattern or a wine rack pattern. In other words, they're offset laterally from the wells in the upper Wolfcamp, and these are labeled M for middle Wolfcamp. And so we've got these 5 situated here. The lateral well spacing between each individual well is 660 feet, and then the distance between the upper and middle Wolfcamp here is 325 feet. And then there's one more thing, which is the most important thing that I'm going to talk about, which is this well here. This is the 6TW. This is the slant well from which the core was acquired. So you can see it tracks down here and it goes very close to the 6U, and then it comes down here and goes close to the 6M. So the closest it got to the 6U was around 85 feet. And down here in this little picture, which is from Jordan's paper, Jordan Sizobka, this red is the slant well, and then the blue is the 6U well, and then these little boxes, these colored boxes, represent cores 1 through 4 of the slant well. So there's the cores 1 through 4 are broadly contiguous, and they represent 400 to 450 feet or so of core acquisition, and that is equivalent to around about 60 feet of vertical section. So that's just a depiction of what was happening in the upper Wolfcamp, and then in the middle Wolfcamp rather, we had another 2 of these cores taken in close proximity to the 6M. So that's kind of, you know, what we're dealing with and where our core data come from. And really, the project itself is a really big project with many facets, you know, all the way from air quality monitoring up in the, you know, the well vicinities, through to some work that we do, and then analysis of drilling fluids and things like that. So it's a really wide-ranging project, but our part was specifically designed to try to observe hydraulic fractures directly, because there's many techniques that people use to try to get at what hydraulic fracture systems look like and how they're distributed, but they're all kind of remote techniques, and what we wanted to do was to see them directly, and then if we could see them and interpret them, get information about fracture density, orientation, morphology, and spatial distribution. Now, we knew that from previous work that ConocoPhillips had done, that some fracture surfaces, these are hydraulic fractures, provide information on fracture propagation direction. And so we were looking out for that. We were also interested to see if we could see natural fractures sealed with typically calcite cement in the Wolfcamp, and to see if they might have been reactivated during hydraulic fracturing. We were looking for proppant. And then the idea was that the other work that was going on in this overall project included hydraulic fracture modeling. And so the idea was that perhaps the information from our observations could be used to either provide input data or to verify, or both, the hydraulic fracture models that people were attempting. Another thing that was done was microseismic monitoring. There's a couple of papers on that in that 2018 group of papers. And we wanted to see if we could use our findings to provide some ground truth for these indirect diagnostic techniques for picking up fracture systems. And then the last thing was the hope that we could compare cores and image logs and use those to calibrate for future image logs. Unfortunately, the quality of the image logs in the wells in question wasn't so great, so we ended up not really being able to do that. But that was the group of things that we were hoping to be able to accomplish. So just let's talk about what we actually did. We had this 4-inch diameter core. It came out of the ground and was sleeved in this aluminum sleeve, which we then cut in 2 so that we could just remove the top and examine the the core whole. So the core is now slabbed in part, but all the analysis that we did was done prior to slabbing. And you can see this is how it looks when it comes out of the, or when you take the top off the aluminum sleeve. And you can see that it's covered in this drilling mud, this brown sludge. And that is what we were having to deal with. It also gets into all open or parted fractures. And so what we did was we collected the material from all of the fracture faces in the hope of trying to find some proppant, and we'll get to that later. So you can see that there are some fractures in here that I've labeled, these two that are kind of oblique here. These are the natural fractures, and then there's this one here and here that are going more orthogonal to the core axis. These are natural fractures. One of the tools that we use to help us, both in terms of recording the information and in terms of just navigating around the core, was a CT scan. And you can see here the CT scan, what I've shown here is a circumferential unwrap. So it's like almost a mirror image of an image log. So it's just the surface of the core, and they take they take this particular grab from the 3D volume just inside the margin of the core, so you don't get all the surface noise. But it allows you to see the fractures and some sedimentological features really clearly. So here you can make out the bedding pretty easily. You can see it up here as well. And you can see this carbonate concretion. This is probably a little pyrite nodule in here. And then you can see these black lines are the breaks, which are the fractures. And so this natural fracture shows up here. It's got a high amplitude sinusoid, as you would expect. And then here's a hydraulic fracture that goes across, and it's this one here. And we're seeing it cross at a high angle with a lower amplitude sinusoid. And here's another one, which looks like this in the core here. And then down here, close to this carbonate concretion, you might be able to make out several other hairline breaks, and then some complication of the trajectories of these other fractures, which are likely also hydraulic fractures. So this was something that we saw quite often, was where there was something like a concretion or some complication in the bedding, that the hydraulic fractures themselves branched and became more complicated in their geometries. So we measured the fractures and described them all from this whole core scenario, and then we collected the material from the fracture faces to analyze for proppant. So let's have a look now at the hydraulic fractures and talk about what they're like. So this panel is from my paper in that 2018 paper. The 2018 ERTEC series of papers, and it shows a number of hydraulic fractures. And the first thing to note is many of them have these smooth planar faces. They're remarkably planar. And you see this kind of wet mud that's formed this dendritic pattern on here. That's because when we parted the fractures, they were completely parted, but they're kind of glued together with this drilling mud. And so when you pull them apart, they create these dendritic patterns as the mud is sucked apart. But when you clean that all off, these have a remarkably smooth face. Yet others have some surface features. So down here, there's a step here, there's a step here, there's some complicated little steps here, some irregular steps, a couple of irregular steps over here. And then this surface is a little bit irregular. It's going through a coarse carbonate lithology. So all these up here are fine-grained mudrock, whereas this is a more coarse carbonate debrite. And oftentimes the fractures that go through these have a slightly rougher morphology. And then, as I showed in the last slide, sometimes we get these complex groups of planes where there's some complication in the underlying geology. This here is a a sterionet, it's a lower hemisphere projection of poles to hydraulic fracture planes. So you see that all the poles are clustered around the margin, which means that these are subvertical fractures, and they kind of trend close to east-west, if not a little bit around from that, maybe east by east-northeast or something like that, you know. And so they are pretty consistent in their orientation. There's, you know, if you look at the spread here, it's maybe 40 degrees, which is kind of, you know, it's reasonably consistent. So a lot of what I reported in the 2018 paper was methods and just some basic morphologies and information. So the next step was to take this a little bit further. And my master's student, Bethany, has been working on the hydraulic fractures in much more detail. And this is a diagram that I took from one of her posters. And she's got cores 1 through 4 laid out here, and then cores 5 and 6 laid out here. You see this is a diagrammatic version. There's no orientation information in here, but what she has done is color-coded the fractures for smooth, rough, and stepped, and those with twist hackles. So I should say that these are all hydraulic fractures. She hasn't got any of the natural fractures in this diagram here. This is just to look at the hydraulic fracture distribution along the core length, and remind ourselves what the geometry was from our 6U and 6TW. So the 6U's coming down here, core 1 is taken just a little bit away from the 6U, and then we go past, and the place that we go past is closest in core 3. So we notice, if we look at this distribution of fractures, that there's some clustering. There's definitely a cluster around here at the top of core 2 and into core 3, and then maybe some more clusters here. There's a cluster here in core 5. So one question we could ask is this a random distribution? Because we know, you know, random distributions have some clustering, or is it a more organized clustering? And is there any effect of proximity to the stimulated wells? Because obviously, if we get close to a stimulated well, we might suspect that perhaps the clustering would, or rather the number of fractures that we were observing might pick up. So we could look at this and make suggestions, but a better way to do this is to do some quantification. And so that's what we did using a technique that was developed by our group at FRAC called the Normalized correlation count. And it's really a variant on a 2-point correlation integral. I haven't got time in this talk to go through exactly how it works, but this paper down here by Randy Marrett et al., that's you know, with me and Lionel Gomez, and so we and Steve Laubach, we document in this paper the details of the normalized correlation count technique, and also provide a link to MATLAB-based software that's available free at this GitHub site. So you can download that correlation count software if you want it, and use it. And obviously you need to read the paper to understand what that's all about. So basically what it does, let's just look at these diagrams for a minute before coming back to the bullets. I've got 3 little panels here that are kind of stick plots of fracture or organization. So they're just fractures that are parallel to one another, and you can think of them as along a scan line or along a well bore or something like that. And the top one is a random distribution. The middle one has 2 organized clusters, and then the bottom one is even spacing. And so what this whole effort does, that's described in the paper, is to show how we can quantify the spatial arrangement by comparing the organization that we observe with a random distribution. So we're quantifying the spatial arrangement by normalizing to expected values for a random distribution. And you can put, you can have data input from outcrop scan lines, thin section scan lines, image logs from horizontal wells in particular. You can include spacing and aperture size. There's a lot of variations that you can do. You can do time series with this. So it's quite a good technique for analyzing spatial organization. And so, as I say, I haven't got time to go through the method or the plot and exactly what it means, but I want to give you a flavor of what the output would look like. So this is just for the upper Wolfcamp cores 1 through 4 data. So we've got here a very intuitive plot, which is a fracture intensity plot. So this blue line refers to the number of fractures along the scan line. In this case, it's been normalized to what you would expect for a random distribution. But how you can read it is just that you see this big group of peaks in the middle indicates that we have that large fracture cluster that we observed. And then there's another cluster out here. If we go over to the normalized correlation count plot on the right, it's a log-log plot in this case. You can choose different kinds of plots. You can have linear, log-log, linear, and so on. But what we're looking at here is the correlation count, which effectively is measuring the number of fractures at a given length scale spacing. So down here, we've got this length scale. We've got 1 here and 10 meters, 100 meters. And what we've got is the blue, which is the data, the observations, the green, which is the randomized version. So that sits along the, and this is a kind of a Monte Carlo simulation of 100 runs of randomizations. So it sits along this one line, and then we're going to normalize the blue to that green line. The gray lines are the 95% confidence limits. And so how to read these plots is that anything that pops out beyond these gray lines is statistically significant. And what it means is that at the given length scale, where you have a peak that sticks up, there are more spacings at that scale than you would expect for a random distribution. And what you can see in this plot is that although there's a lot of up and down, peaks and troughs, many of these peaks are up above this 95% confidence limit. And when you get out here from about 2 meters onwards, there's a plateau. It, albeit weak, it's just sitting above the 95 confidence limits, but it's nevertheless a plateau outside of those. It's indicating that at all these length scales, there's more fracture spacings than you would expect. And this is a typical plot that you see when you've got what we would describe as an extrinsic or forced organization of fractures. And in this case, we think it's because the fractures develop from the stimulated well, and then when the slant well gets really close, you see an uptick in the number. But it's interesting that there is some structure in this, and so there is a hint of some regularity of spacings or regularity of clusters at these smaller length scales. That's all I'm going to say, because we would need to back up and explain how to generate these plots in order to get more out of it. But for the points of this talk, I just want to say that we can analyze this spatial distribution using this technique. So in this next slide, I've shown the same diagram that I showed before from Bethany's poster. And then I've just got some data here about the completions. So for all those 11 wells, there were between 37 and 49 stages per well. Each stages are around about 200 feet each. And then the perforation clusters were designed in different ways for different wells. In the case of the 6U, there were 3 perforation clusters per stage. Some other wells had 5. Sometimes they alternated between 3 and 5. But for here, where we're interested in, close to the slant core, we have these 3 perforation clusters per stage. And I've borrowed a picture out of Srivastava's paper. He's in petroleum engineering here at UT, and this is out of his SBE paper that I've just put down here. And it's a similar idea to Bethany's. This is the slant core here, and what he's showing is hydraulic fractures in red. This time he's got natural fractures and what he's called NR, which is natural reactivated, in this data set as well. But it's essentially the same as what Bethany's shown up here. And you can see a whole lot of red around cores 2, the end of core 2 and into core 3, and then some pick up in core 4 as well. But here in behind, designated AUWW, is that 6S well, the stimulated well in the upper Wolfcamp. And you can see that there's 2 stages represented here, each with the 3 perforation clusters. So you've got stage UWC, a stage UWB, blue and kind of brown color, representing the perforation clusters. The perforation cluster is 2.5 feet with 6 shots per foot. That's the way they did this. Now, let's just do a thought experiment here. Assuming each shot creates 1 hydraulic fracture, then we would have 45 fractures per stage, because we've got 3 perforation clusters and we've got 6 shots per foot in here. So that's, 15 times 3 makes 45. And then for 2 stages, for the whole of the distance core 1, 2, 3, and 4, we would have 90 fractures. Now, in cores 1 to 4, which is around about 400 feet, there are 324 hydraulic fractures. So we're going to compare this number with this number, and you can see right away there's a lot more hydraulic fractures than you would expect. Now, I've put this little line here in italics because this word here could be problematic. We are assuming each shot creates 1 hydraulic fracture. Now, in the literature, that's what a lot of people say, but that's something that is a premise, and we would want to question that later. So just bear that in mind. But if we just assume that as a simple way of thinking about the problem, then we're creating far fewer fractures in our thought experiment than we actually observe. So why would that be? And that's really where Bethany comes in with some of her work, because one of the ideas that we had was that some of the ways that the hydraulic fractures propagate may lead to having more fractures than we might expect based on the number of perforation clusters and shots that we have. Bethany put this slide together to show that, you can have diversion here along bedding, diversion along a natural fracture, diversion along a concretion, but perhaps rather than diverting, you might generate 2 strands. So part of this fracture might continue on and part might divert, same with the bedding situation. So it's possible that during diversion, you could generate more than the initial fracture. Also, there are mechanisms for segmentation, such as these twist hackles here. And I'm going to come back and show this diagram a little bit larger in a second. But essentially, there are ways that fractures grow. And you can see this in outcrop. It's not just, it's not hydraulic fracture specific in the ground. It's any fractures in rock will have these kinds of features potentially. And then lastly, we've got this potential that a single parent fracture bifurcates. So gray here bifurcates in fractures A and B, shown in the pink and the green. She looks at our hydraulic fracture data set from this project, but she's also done a lot of work looking at these hydrostone and gypsum plaster block models, where here's the well bore, and they've created these little perforation clusters here and fired the shots and generated all kinds of interesting structures in these plaster block models. So this is John Olson's lab over in petroleum engineering. So Bethany has analyzed a lot of these block models as well for the kinds of structures that she had observed in the slant core. So let's have a look at them then in the slant core. First, we'll just look at bifurcation. So here what I've done is I've shown the whole core cleaned up nicely, and you can kind of see the bedding traces here, just very subtly. And so red is on the right. So this would be uphole. To your left, as you're looking at this screen, would be uphole. And so because uphole is north, then this direction over here is to the west. And so we think that this is an indication of fracture bifurcation, where the bifurcation initiated just out of the core above the screen. I've pulled apart the core here so you can see all these little discs and you see the fracture faces. There's some steps on this one here. But this kind of structure where you get these two closely spaced but not quite parallel hydraulic fractures is really quite common, and it was described previously by the ConocoPhillips group when they looked at an Eagle Ford core that was a similar experiment to this one, a core through a stimulated volume. And they found these kinds of things as well. And they termed them doublets. So we carried on with that nomenclature. And since we've done this work and looked at, there's been two other hydraulic fracture projects other than this HFTS1, we've gone through into phase 2 and then a different project. We've seen triplets, quads, quints, and even there were 6 together that suggest bifurcation. In this case, you can get the propagation direction, so as I mentioned, north is uphole and north is to the left. So this would be propagation towards the west. And so Bethany's done a lot of work analyzing all the cases where we had these and come out with some plots. I'm not going to show this now. This is for her to present another time. I mentioned these twist hackles and surface markings. There are some, sometimes they can be really subtle. So I've just dashed the line here. This is the line along which they start. And so the propagation is coming along nicely in a single master fracture. And then all of a sudden you get all this segmentation. And the same here. You get all the segmentation, and you can infer local propagation direction as well. So this, I'd put this in just to remind me to say that this kind of illustrates a concept whereby if you're growing a fracture, you have to remember that it's not just growing in one direction. It's growing laterally, but also up and potentially down. So, but depending on where you capture that fracture, you might see propagation directions that don't necessarily make sense when you're thinking about the proximity or the direction towards the simulated well. You might think, oh, well, this should be easy. All the fractures that are above the stimulated well should be propagating upwards. All of them below should be propagating downwards. But that's not how it works. And in particular, if you've got this segmentation, if you've got diversions, if you've got complexities, then you can have situations where you're capturing a propagation of a hydraulic fracture that looks like it's going in the wrong direction. So having a three-dimensional idea of what's happening is actually really what you need to be doing. And having said that, I should just mention that Bethany, together with Robin Domiser here at the Bureau, they have really gone quite far in creating a really nice geomodel for the hydraulic fracture test site. And what they're going to do next is to try some hydraulic fracture modeling that's conditioned to the specifics of the stimulation and the geology. And then they can compare that with what we observed. I said I'd mention the natural fractures. There's 2 sets of calcite-filled natural fractures, and I described them fully in 2 papers, one in the ERTEC 2018, but I had another one in the following year specifically about natural fractures. But just briefly, they'll look like this in this top right figure, or like that in the bottom right figure. So, and this is just simply whether they're parted or not. We use that term parting to mean that the faces are parted now. Now, why that is a question, and I'll come to that in a bit. So you can see this calcite on the surface. There's matching calcite on the other face. And then down here, we've got a natural fracture filled with calcite that's segmented, but it's intact. So it's not parted, it's intact. As I mentioned, there's two sets. This set one is the most common. Northeast, southwest, here's the stereogram of that. Again, poles to plains. There were 197 of these in total in the core. 38 of them were parted, so that's 19% of them were parted. Now, 2 of them have these euhedral calcite crystals on the surface, and that is a strong indicator that they were probably open in the subsurface. And they're close to 1 millimeter each, 0.89 and then around about 1. And we think that that's obviously a minimum value. You measure the thickness of the cement on each surface and summit, but so we don't know what their apertures were in the subsurface, but they were likely open. For set 2, which is west-northwest, east-northeast, there were 112 of these, not quite so many, but 46 of them were parted, so that's now 41%. And what we thought was this orientation is just a little bit closer to the hydraulic fracture orientation, and maybe it's a slightly more favorable orientation to be reactivated. We saw some faults. There were 2 types of fault to recognize. There's this soft sediment deformation with this nice faulting here, and then there's later faults where I've shown one here. These are CT scans. This one down here is from the core, and you can see the slicken lines on the surface here. Mostly they have normal and dextral components, oblique slip, and some have a small amount of calcite cement. We didn't see too many faults, but there were a few. One thing that people were really interested in was whether bedding planes were going to play a big part in the hydraulic fracture system, because people have surmised that bedding planes could be weaknesses, they could be places where hydraulic fractures divert. Now, to cut to the chase, in this core, we did not see many cases of bedding reactivation at all. And we didn't see bedding parallel fractures either, generally speaking. So when I say bed parallel fractures, I mean natural bed parallel fractures. So what we've got here is a relatively unusual case. I wouldn't say rare, but they're not that many, where we've got a bed parallel parting, and it is pulled apart here. And you can see there's nothing on this surface. There's no calcite cement. And moreover, you see this mud, it's only on the bottom here. And then there's a couple of dribbles that have gone down as this core has been turned over. So it's really not even got mud in there. So we think that this is probably popped open during core retrieval, not even during drilling, because if it was open in the subsurface during the drilling process or as a hydraulic fracture reactivation, then it would have mud all along it. So, you know, well, we see a few of these examples where we see the parting along the bedding, but we're hard pressed to tell why the fracture is now parted. And that's the same with all the fractures that are now parted, all the natural fractures as well. Because we don't know if it's to do with hydraulic fracture reactivation, drilling-induced, or subsequent core handling. So it's hard to distinguish those. Lastly, the proppant study. Sarah wrote all this up. It's a huge effort. And so if you want to know about proppant in this core, go and read her 2018 paper, the ERTEC paper. Here in the top picture, we've got a 3-foot length of core with a NF-HF complex, that's natural fracture, hydraulic fracture complex in the middle. And then at the end, it's a rather out of focus at the end, but there's a little doublet there. And that little doublet happens to have a sand pack. And so the sand patches are on the upper face of that doublet, and you see them here. So this pale material here is sand. You can kind of just about make out the sandy texture. And so we labeled these patches. There's not really much mud around here. There's sometimes mud. You see where it's a slightly darker gray, is a little bit of mud, but not very much. And these patches we think are intact. So they were there before the drilling. And then there was another place here in the CT scan on the left, and here looking at one of the fracture surfaces, where you see a thick accumulation of sand, and it's largely just sand here. There's mud here that's separate from it, and some has got entrained in the mud right here. And then this is all aluminum swarf down here from cutting the tubes apart. But you see this is about 1 centimeter wide in total. If you look at the CT scan, though, you can see that it's not just one fracture. There's a group of fractures, and this dark gray material in this fracture here is the sand. You can imagine it would have a kind of a mid to dark gray color, given that it's sand, and here's the carbonate and mudrock, host rock. So you see that the sand is caught up in this complex area. The other place where we found a pack was also in a complex area where you'd got a big concretion and you'd got a number of fractures diverting around it, rather similar to that very first slide that I showed with the CT scan, where those fractures were going around the carbonate. It wasn't that one, but another one similar to that. We surmised that perhaps sand gets caught up in these complex areas, but you could also say, well, it gets preserved here because it's complicated and it doesn't get washed out during the drilling process. So there's a lot of interpretation uncertainty in terms of, where if you don't see the sand, you don't know whether it was there but got washed out during drilling, because there's certainly background sand in all the drilling mud. So to wrap this up, we've got more than 700 fractures total. That's hydraulic fractures, natural and everything, were found in 600 feet of core. And we can distinguish them using criteria that I spelled out in the 2018 paper. I didn't really talk about them much here. So we've got hydraulic fractures, we've got 2 sets of calcite-filled natural fractures, and then we've got drilling-induced and core handling that we can all hopefully tell apart. The hydraulic fractures are clustered and they seem to have some kind of organization. There's been some studies trying to look to see if you can match the hydraulic fracture clusters with the perforation clusters, but I would say that it's a bit of a stretch. Some people think they can see a pattern, and other people, I'm kind of more on the more hesitant group, but certainly there's potential for doing that kind of analysis if you have these kinds of data sets. But in any case, we could definitely see there was an uptick in the number of hydraulic fractures per foot closest to the stimulated wells. And there are more fractures than you would expect if you made the assumption that there would be 1 fracture generated per shot. Now that is an assumption and it might be wrong, so we have to be careful. But we do know that there are mechanisms, including bifurcation, segmentation, also possibly diversion, that could cause you to have more fracture strands than you would expect. We see parting of natural fractures, and we infer sometimes, especially if we've got a hydraulic fracture very close to it or impinging or apparently diverting along it, that it's a reactivation during hydraulic fracturing. But oftentimes the cause is inconclusive because it could just have parted during drilling or afterwards during a core handling. We saw very few bedding parallel breaks, and most of the ones that we saw, we were pretty convinced that they were to do with core handling. We did find proppant patches and packs that we think were in situ prior to drilling. And as I say, Sarah did a whole study about that. So that's the conclusion, I want to acknowledge the DOE funding that was supported our work, and the overall consortium that made the project possible. Jordan at the GTI provided all the project management help, and like I say, he was the one that wrote the overview paper. Laredo Petroleum was the operator, and they really went above and beyond, providing all data and help. Seth Bussetti and Helen Farrell at Conoco, and then Helen used to be at Conoco, but she had a consulting company at the time. They also did a simultaneous analysis of the core, and they provided fracture orientation data. We kind of worked in tandem, and they did that part, and we did other parts. So thanks to them for the actual orientation data. And then Core Labs did the CT scans, and everybody helped with, you know, from the consortium, help with input on interpretation. So that's, you know, and I'm supported generally by the Fracture Research and Application Consortium, as is Bethany. So that's the end of the kind of presentation. So I guess there's a few things in the chat. So perhaps Sahar could manage those, and we can go through them.
Thank you very much, Julia, for your great talk and what you have done on characterization of fractured hydraulic fractures and their propagation is very amazing. So I see several questions in the chat. The first one is from Aaron Rodriguez. Aaron, would you like to unmute yourself and ask your question? Or I can read the question.
Yeah, I see. Actually, Jeet had a question before that. Oh, he sent it to me privately. Okay. Oh. Yes, Jeet, if you send the question privately, nobody can see it. So what I'm going to do is I'm going to answer Aaron's question first, or try to, which I probably can't actually, because I see what he's asking. He's how far away from the nearest cluster were the sand-filled fractures observed in the core? I can't answer that off the top of my head, because I'd need to go back and look at the geometry of it. And I don't know, so I'm sure somebody figured that out. It's more than 85 feet though, because we were the closest at 85 feet. However, the fractures were observed fairly near to the closest. So, you know, I'm going to say around about 100 feet is a rough estimate. I don't recall the exact number. I'd have to go back in and look. And then I'm going to go back up to Jeet's questions. So he asks, why are the hydraulic fractures planar? They're not always planar. But the simple answer is that they just propagate parallel to the maximum horizontal stress and the vertical stress. So they're a planar subvertical feature. Now, of course, if they come to any place where that stress field is perturbed, then they may change slightly in direction. They may kink, particularly at bed boundaries, that kind of a thing. But where you capture them, typically you're in a reasonably homogeneous rock, and so you know, with 4 inches, I mean, yes, there's heterogeneity at all scales in mudrocks, we know that, but mechanically, quite commonly, there's reasonable homogeneity in many parts of that core, and so those hydraulic fractures just grow parallel to SH max.
Right, thank you, Julia. So the next question.
Yeah, he had a bunch of questions though.
Yeah.
So maybe I should go on to somebody else and then come back to him, so it can be fair.
Okay.
So Bill's asking, what was the ratio of shear to tensile fractures among the natural fractures? And what is the proportion of drilling-induced, core handling-induced fractures to hydraulic fractures? Yeah, okay. So I can't give numbers to to any of that without, you know, I could if I went in and looked at the numbers and calculated it. But basically, we saw very few shear fractures. By that, the only ones that we would see are faults. So there were, I don't know, a handful of faults, whereas there were several, I can't remember what they were. It's like 100 and something and then 100 and something else for the 2 sets of natural fractures. So there were a handful of faults and hundreds of opening mode fractures in the natural fracture data set. And then the proportions of drilling-induced core handling, I don't have the numbers off the top of my head, but if we say there's 700 total, 300 of them, I think it was more than 300, were hydraulics, a couple hundred were naturals, and then, you know, about half each drilling-induced and core handling. Now, I didn't talk about the difficulty of telling drilling-induced fractures apart from hydraulic fractures, and that is really quite tricky because the drilling-induced fractures will also grow parallel to SH max. And so that can be really quite difficult to deal with. We did develop some criteria along with the ConocoPhillips people, looking at where you see fractures that have symmetry with respect to the core. Who's talking? Somebody else is talking. Anyway, you know, we had a fair amount of, well, so in the descriptions that I did, I had uncertainty indicators where, you know, I was sure, probable, best guess, and quite a few times with the drilling induced versus hydraulic fractures, it could be a best guess, where you're trying to look for core symmetric features to indicate drilling induced. Because if the fracture is symmetric with respect to the core, or has symmetric features like plumose going all around the margin, it's very suspicious. You would have to just luckily capture the feature in the subsurface that with the core just right there to make it symmetric. Whereas it's a much easier idea that, well, you just made it with that core and it's symmetric because the core captured it in such a way to make those features. So you know, that's really what we did. So I hope that kind of answers the questions. The information is there in the papers about the methods for that. Juan asks, thank you, David, for saying great talk. Juan asks, does the random function you generate count for the internal anisotropy of the layer? No, I'm not quite sure where this question is going. So the correlation count is a numerical method for assessing if there's a random distribution or not. So I think where you're going there is, wouldn't you expect different fracture clustering or fracture organization as you go from layer to layer? And you're absolutely right. So this was one of the frustrations of the project, was that the core is slant. So you're mixing proximity to the stimulated well and the going through different layers. So you could ask, well, is that clustering because you went close to the stimulated well, or is it because you went through a layer that happens to take hydraulic fractures much more readily? And those two things, you know, are two possibilities, but you couldn't distinguish those in the data set that we have. You may be able to kind of answer it with looking at the microseismic, but the microseismic also throws up its own whole kind of can of worms as to how you identify, how you interpret any of the events. So, you know, it's tricky. So I think the point is well taken, that analysis of this kind needs to take into account that you're going from layer to layer. One thing you can do is, if you think you're going through layers of different composition, is you can separate out the data for all the data that was in layer 1 and all the data that's in layer 2. Now, of course, you might not have enough data to do a really good analysis, but yes, it's a good point. Michael Gross says hi Michael, and Aaron says thank you. Michael has a question now. He has two questions, in fact. Are you able to match the hydraulic fracture distributions with microseismicity? Well, kinda. but not very convincingly. So Neil Stegent from Pinnacle, which was then Baker Hughes, I guess, at the time, they did, no, Halliburton, wasn't it? Not Baker Hughes, Halliburton bought them. So they did the analysis of the microseismic data, and they kind of hinted that there might be some link between the two, but there was really a lot of uncertainty, especially when it pertained to fractures from different stages, fractures even from different wells, and which ones were relating to which parts of the data set. So yeah, there was some indication, but not very convincing. And then the second question is, in thin section, can you identify microcracks that formed due to hydraulic fracturing? I would say that that last thing, well, first of all, we didn't try it because we did not sample. It wasn't part of the work that we were allowed to do or thought of doing. I think you'd be very hard pressed to do that. The only way that you could do it is to mark the fluid. But even then, you know, I mean, and then we get into the whole question of, are the hydraulic fractures linked to the fluid-filled hydraulic fracture network, or are they far-field hydraulic fractures that are dry, you know, that just develop because of the stress change due to the hydraulic fracture treatment? And so I would have, yeah, it's going to be a really rough deal to distinguish those from things that might have developed during drilling or subsequent core handling. It's going to be very hard. So we didn't do it and we didn't attempt it, but I would think that it would be very difficult to do. There's another question. How are we doing for time? Got 5 minutes. I'll try and race through these. Did the researchers compare between the well angle and the fracture distribution and frequency? I'm not quite sure what you mean by that, Mohammed. Yeah, I'm not quite sure what you mean by that. We just had we had a slant well that had a particular, I don't recall the exact angle, but it was around about 8.5 degrees, I think, off the horizontal. And it was pretty consistent. We thought there might have been a little bit of deviation porpoising up and down, but not really very marked. We could see a reasonably consistent tracking through the bedding as we went down through the core. Fractures shot across bedding planes, do you think that would be typical in thin bedded rocks in general, or this is Tody's question, or does diagenetic calcite in the rock have more of an effect than weaknesses? Yeah, I mean, this is a good question. I think in general, that's the way that they tend to behave. Now, I can say that in another experiment that we did where the angle of the slant well was steeper, that we saw a lot of breaks in the core along bedding, but we thought that was to do with the angle of drilling and not, you know, it's not to do with the hydraulic fracturing. So I think hydraulic fracturing in generally speaking is ignoring that bedding. Now, is that the case everywhere? I don't know. There's likely to be a difference in behavior close to the wellbore versus very far away because the energy of the fracture will be different. When you're close up, you might expect it to blow through everything. When you're further away, when it's weak and pathetic, it might decide, oh, I've got to this bed and I really just can't go through it, so I'll just divert along it. So there may be differences. We obviously only had one snapshot. Tongwei asks a question about bedding also. Do you think the meter scale lithofaces play a role? Well, like I say, we can't answer that with just this one snapshot, but there's likely to be differences close and further away. Let's see, Mosen. Of the 700 fractures, were only 2-fold were sand? No. So we only had 2 packs, sand packs. We had another handful that were filled, or were not filled, but had sand patches. So like that first picture I showed where you just had patches. And then every other fracture had sand in it. Now, in that case, most of it was entrained in the drilling mud. But the question is, was it in there to start with, or did it just get swept in during the drilling process because elsewhere the mud has entrained sand from a pack and pushed it around and then homogenized it and got it in there. So if you read Sarah's paper, she's got all the details about how much sand was in and what sizes. You know, they pump 40-70 mesh and then 100 mesh, and she's got all the size ranges for all the fractures faces. So no, all of them had some sand, only 2 packs, I think, and then some patches. Peter, with the vertical section transected by the core and associated logs from the slant or other nearby wells, will you be able to develop a mechanical layering characterization within which to assess fracture growth? Yeah, that's really kind of what Bethany and Robin Domiser are doing by building this geomodel. And the idea is to be able to put, you know, all the information that we have about the layering. Now, of course, you get into questions of what scale you can depict, you know, what's the smallest grid size that you can use and all the rest of it with the modeling. So it's tricky, but yes, that's exactly what they're trying to do. And then they're going to try and do some geomechanical modeling of the hydraulic fractures and see what they get. Islam, awesome work, thank you. Oh, okay, that's just a compliment, thank you very much. Zach asks, how do you tell the difference with with natural fracture versus shear fracture? So the natural fractures have calcite cement. And when we look at that calcite cement, we usually look at it with a hand lens or with a pocket microscope or something to try to assess what kind of cement it is. Some of the fractures in other places that I've looked at have fibrous calcite where you can track shear. But in this case, they're all blocky and they have no indication of shear whatsoever. So the calcite there, you look at the, you know, obviously if it's intact, you can see whether there's any shear. You can also look if it's parted at the cement and try to see if there's any slicken sides or anything like that, or slicken fibers in the cement. So that's how we do that. And now the shear fracturing induced by hydraulic fractures, that's when you reactivate a natural fracture. The thing is that it happens quickly, and so you'd probably only see slicken sides. You wouldn't see slicken fibers. We didn't see any evidence of that. We looked for any trace of criterion that we could use. Sahar, we're at 10:02. I can talk for a couple more minutes. I think we're near the end of the questions anyway. Yeah, we've just got, maybe I'll just do that. So Bo has one question. Both natural and hydraulic fractures are so complicated. Just curious about the implications of the work on fracturing simulated development. Yeah, so what we're going to do is we're going to try and work with our companies that support the Fracture Research Consortium and John Olson's group to look at the kinds of hydraulic fracture simulation that they do, what's commercial, what they use, what they develop in-house, plus what John Olson's group has developed in terms of 3D hydraulic fracture simulators, and try to just iterate and improve them. That's really part of the goal. And obviously, if we can do it using situations where we have some possibility of verifying the modeling, then that's even better, because that's usually a big problem with anything you try and do in the subsurface. Is you can come up with a fancy model or an effort to simulate something, but if you can't verify it, then you don't know whether you're right or if you're right for the wrong reasons. So that's something that we worry about a lot with fractures, because there's all kinds of ways of saying, well, this is what I think the fracture network is like, but actually then verifying that is really pretty hard. And so we're looking into different ways of doing that. So, you know, improved characterization of the hydraulic fracture network, perhaps using the AEC contrast agents that Mosen works on, David Chapman, or improving the hydraulic fracture stimulation modeling efforts. So that's probably it.
All right, Julia, thank you very much for addressing all these questions. Do you need to address any other comment? We can extend it for a few.
No, I think that's it. That we come to the end of the questions here.
Okay, perfect. So, thank you very much for your time, for your great talk, for joining us today.
All right. Well, thank you, everybody, for joining in. I've seen some friendly faces, people I know, and some people I don't know. So thank you very much, and see you soon, hopefully, for real.
Thank you. Thank you, everyone, for joining us. See you next week.